Hello everyone. Uh, in the previous lecture, we just tried to work out few examples, right? We tried to understand the group Z mod n Z for certain specific values of n. So I think we started with Z mod 3Z, right? Yeah, we we got started with Z mod 3Z. Then we went on to the group Z mod 4Z, and I think I also, yeah, I did give certain bunch of exercises for you to work on. All these exercises is related to the notions that you have already learned so far. Okay, these examples or other kind of if you work on these examples, that will help you to strengthen your understanding some of the notions that you have already met. For instance, we have met the notion of a subgroup of a group. It makes perfect sense to ask the following question: that given a group G, how many subgroups do you have? How many subgroups does that group have? And can you describe all the subgroups? This is a difficult question, certainly. I mean, in its complete generality, but for specific examples, for instance, for Z mod 3Z or Z mod 4Z, and there are other also, how to say, examples, other examples of groups that can be treated using in a very elementary approach. Okay, so please work on these exercises. That will really help you to understand uh, one of the most important notions that you have met in this course. First of all, I mean, you'll get a chance to revisit the notion of group, and then you'll have a chance to revisit the notion of subgroups. Then again, you'll have a chance to visit the notion of cosets, namely left cosets and right cosets. And just as I have mentioned, in abelian groups, the notion of left cosets and right cosets, they coincide, right? I hope I did mention. If it is not printed in this lecture, I think I wrote using this red marker. Okay, the fact is that okay, I'm not able to locate it from anywhere, but anyway, so let me just try to quickly recall what I just stated, maybe before getting into the content of this. So I said that if you have a subgroup H, if you have a subgroup H of a group G, then corresponding to an element little g inside G, you can consider this coset GH. You can also consider this coset HG. I'm claiming that these two are equal. I'm saying that these two are equal. Sorry. So given a subgroup H of G and an element G in G, I'm claiming that GH is same as HG. I'm saying when G is abelian. Okay, so please try to see that this is indeed the case. This is really easy to see. Okay, this just uses the definition of the of an abelian group. Okay, nothing beyond that. Anyway, so going back to some of the things that we have already discussed is following exercise or question, which asks to consider the two groups, namely this group U2R. Okay, so recall that this group U2R consists of matrices of the form 1x01, where x is a real number. Okay, and this forms a group under matrix multiplication. Okay, so the question was that whether the group of real numbers and this group U2R, whether these two groups are really different or not. And as I said, practically this is almost impossible to answer this question, because the notion of really different is not a well defined property, right? So I just stated this exercise or this question in order to uh, uh, I wanted you to work on this problem so that maybe you develop some sort of intuition or some sort of understanding. Okay, and now I'll try to answer this question. I try to solve this exercise, but as you get to see, this cannot be solved. Okay, because this doesn't have any precise answer. Instead of having a solution here, we can have a discussion. Okay, so let's see what can we do in this context with these two groups, namely U2R and this group R of real numbers. Okay, so note that if you consider the group of, I mean rather the set of real numbers, that we know that it forms a group under the law of addition, right? Given two elements x and y, we obtain x plus y by adding, adding them, right? We apply the composition law on the pair x comma y, and we end up getting the sum x plus y, right? This is the composition law, and you know that the set of real numbers form a group under this composition law. On the other hand, this group U2R, as I mentioned a while ago, that it consists of matrices of the form 1x01, where x varies in R, right? and this group forms, this set forms a group under matrix multiplication. Okay, and now if we pick two elements 1x01 and 1y01 from this group, then you see that their product, okay, when you compose them using the composition law of U2R, which is matrix multiplication, then what we get is 1 x plus y 0 and y, right? So what you see is that if you pick two real numbers x and y, then applying the composition law on the pair x comma y, you end up getting x plus y. On the other hand, if you pick two elements 1x01 and 1y01 from U2R, if you apply the composition law on this pair, okay, on this pair, then you end up getting 1 x plus y 0 and 1, right? So I mean, there is some, how to say, in some sense you see some sort of similarity between the composition laws of these two groups, right? More precisely, between the structure of these two groups, right? So this can be made precise, and that is what we are trying to do today in today's lecture. Okay, so let me introduce this notion of a homomorphism between groups. So if you start with two groups G and G prime, then a homomorphism phi from G to G prime, there is a map satisfying the following condition, that phi of AB is phi A times phi B. Okay, it happens for all AB in G. Okay, let me repeat that phi of AB is phi A times phi B. Okay, where phi is a given map from G to G. We want that phi of AB is phi A times phi B for all AB inside G. Okay, in such a situation, this function phi from G to G prime is called a homomorphism from G to G prime. Okay, so homomorphism phi from a group G to a group G prime is a map that satisfies this condition. Okay, very roughly speaking, one can say that homomorphisms are the structure preserving maps between two groups. Okay, or structure preserving the homomorphisms are the structure preserving maps from a group to another group. Okay, so sometime to indicate that we have groups in mind, we use the phrase group homomorphism instead of calling it a homomorphism. Okay, so whatever you're considering, these are called group homomorphisms, and just to abbreviate, we'll call them homomorphisms only. Okay, sometimes we can also use the phrase group homomorphism. Okay, anyway, so let me try to move on. So the question that we had is about this group U2R and this group of real numbers, right? So maybe so as we saw that when you pick two real numbers x and y, by composing them, what we end up getting is x plus y, and then if you pick two elements from U2R 1x01 and 1y01, by composing them we end up getting 1 x plus y 0 and 1. So in some sense, if we consider x and 1x01 as the same thing, okay, so what I'm saying is not precise, it's somewhat naive. I'm making this comment just to make sure that just to make sure that you understand these comments are somewhat naive as of now. Okay, but if there is a way to identify this real number x with 1x01, with that matrix 1x01, okay, and if you could somehow identify y with 1y01, okay, then if you compose xy, then you end up getting xy. On the other hand, what the elements with which you have identified x and y, if you compose these elements, then you end up getting 1 and then x plus y 0 1. Okay, and so identifying x with 1x01 and y with 1y01 and identifying x plus y 1 x plus y 0 1, more precisely, if you take, let me just write, if you take a real number c, if you identify it with 1c01, okay, so some sort of if we okay, let me not use the word identify because it may sound something like the identity. Okay, so if you considering the real number c, and the matrix 1c01 as the same, okay, and as you know, a real number cannot be a 2 by 2 matrix, so let me put it in quotes. Okay, so if you consider c and 1c01 as the same, again for any c in C, then what you see is that then what you observe is that uh, I mean, when you pick two real numbers x and y and compose them using the composition law of the group of real numbers, then what you get, and with which these numbers have been identified, namely 1x01, 1y01, and 1x plus y01. Okay, so there you see that if you compose these two, you end up getting this. This is precisely what I have just mentioned while defining homomorphism. Let me repeat. So in math, to consider something as the same or somewhat, I mean, or to relate something, to relate an element of a set with the element of some other set, okay, what you do is to consider a function, right? So that is what you are going to do. So you are going to define a function from R to U to R that sends or the real, I mean, a real number x to 1x01 for any such, for any real number x, okay. And then what I have been explaining in terms of composing x and y and then composing the elements corresponding to x and y. In other words, what I was explaining is that so you take x and y and then compose them. So how do you compose them? By adding. On the other hand, uh, if you take the matrices with which you have identified these real numbers, in other words, if you take these matrix psi x and psi y and then compose them, so right now instead of adding we will multiply, so then these two things should be the same, right? More precisely, the matrix to which this number corresponds is same as this. In other words, psi of x plus y is equal to this, okay. This holds for all xy inside R, right? So this is something that you already see and you already also saw, okay. This is a, this equality for all real number x and y is a simple, sorry, let me just erase it out because I don't it's good to write things in words. Yeah, it is easy to see after doing an elementary computation using matrix multiplication that this equality holds for all xy inside R, okay. And then if you just go back to the definition of a homomorphism, then you see that we have precisely, how to say, encapsulated this feature into this definition, okay. And this map psi certainly does have this feature, okay. This is something that one needs to observe, and this is precisely this exercise, right? If you, I mean, if you want, I have already solved this exercise by while discussing, right? Yeah, but still, write down a solution of this exercise, and you. So this says that this map psi, as we defined below, is a group homomorphism. Okay. In other words, psi of AB is psi A. So you need to show that psi of AB is psi A times psi B. In other words, I mean, to be more precise, psi of as I've already noted, that psi of A plus B, or maybe psi of x plus y. Okay. Psi of, okay, just let me write it in terms of A and B. That feels probably better. That psi of AB is psi of A times psi of B for all real numbers AB inside R. Yeah. So what you need to prove is that, or what you have already observed probably, okay, we do some elementary computation using matrix multiplication, nothing beyond that. That psi of AB is psi times psi B, okay. Again, you can ask me to be more precise here, or you can ask me what do I mean by A times B. Of course, of course by A times B I mean A composed with B as per the composition law of the group R, okay. So which is A dot B, right? Dot means usually the standard notation for the group operation, but here specifically for the group of real numbers we have this law of addition, right? So you have to show that psi of A plus B is same as psi times psi B. Let me also put a dot here, and then let me remark that this is addition law of the reals, okay, and this is matrix multiplication, okay. So this is matrix multiplication and this is addition. And as you see here, the psi of AB is psi times psi B. So there is some sort of concern or care that we need here, okay. For example, so when you write A and B next to each other, that means that we are composing A and B. So here A and B comes from G, okay. So here this AB denotes A times B, where dot, how to say, where this dot is the, oh, this is terrible actually. This dot is the composition law of G, right? is the composition law of G. And here when you have 5 times 5, sorry, and here when you have 5 times 5b, it means that you are right, I mean you are having 5 times 5b in mind, where this dot is a composition law of the group G prime. You may note that there is one dot here and one dot here. It may lead to some confusion, so let me elaborate it. So let me use certain symbols to denote the composition law of these two groups. So as I have I have elaborated the definition of homomorphism here in the footnote further. So if you have two groups G and G prime whose composition laws are denoted by the star and asterisk, then a homomorphism phi from G comma star to G prime comma asterisk is a map satisfying phi of A star B is phi A asterisk phi B for all A, B in G. Okay, so if you want, this is the precise definition of the notion of a homomorphism or a group homomorphism. Okay, but very often it is abbreviated in this form. Okay, in this definition 120, the form of definition 120, and from this equality it has to be understood, okay, that when you write A and B, then you have composed A with B as per the composition law of the domain of this A and B, which is G. And here when you write phi A times phi B, then it is implicit that we have composed phi A with phi B as per the composition law of the domain of as per the composition law of the group from which phi A and phi B, to which phi A and phi B belong. So phi A and phi B belong to G prime by definition of this function phi. So when you write phi times phi B, that means you're composing phi A and phi B as per the composition law of the group G prime, right? So here you are composing phi A and phi B as per the composition law of the group G prime. So here you have star and here you have star 2. And before while composing A with B, we have used the composition law of the group G. Okay, great, fine. And so today's lecture revolves around the notion of group homomorphism. And as you see that working on this exercise 122, I mean it's easy. Okay, it just relies on how to say, our understanding of matrix multiplication and not much beyond it, right? So we'll also have several exercises that will help us to improve our understanding of, for instance, subgroups and our understanding around groups, to be precise. Okay, let me not highlight the specific instances that we'll learn across that we learn when you go through all these exercises. So in this exercise 123, this says that if you have a group homomorphism from a group G to G prime, then if you look at all the elements G in G, okay, all the elements G in G which are mapped to the identity element of G prime. Here E prime is the identity element of G prime. Okay, so we have denoted the identity element of G prime by this letter E prime, and then we are looking at all elements of G that are mapped under this map, that are mapped by phi to the element E prime, that is the identity element of the group G prime. And this exercise says that this subset forms a subgroup of the group G. Okay, fine. And the subgroup has a very specific name. This subgroup is called the kernel. Okay, so if we have a group homomorphism phi from G to G prime, then the kernel of phi is the subgroup consisting of all the elements of G which are mapped to the identity element of the group G prime. Okay, under this homomorphism, of course. And yeah, I could have introduced this definition before introducing this exercise, but of course at that time we could not have used the word subgroup. So thanks to this exercise, we know that this is a subgroup. Okay, now we can say that this subgroup is called the kernel. So things are how to say, logical as of now. But as usual, you may say that we still do not have a proof of this exercise. No, we don't have. This is left for you as an exercise to work on. Okay, so please show that this subset of consisting of the elements of G which are mapped to the identity element of G prime, that forms a subgroup of G. Okay, great. So here is one more notion that we will learn today, or maybe there are two more, or maybe just few more notions to be learned today. Okay, I think 2 or 3. So, and of course we will have several exercises on these notions so that you get a chance to work on these notions over and over and over again to in order to familiarize yourself, make yourself comfortable with these notions. Okay. Yeah. So suppose you have a subgroup H of a group G, then you call it normal if GAG inverse lies inside H for any H in for any H in H and for any G in G. Okay. So if you take any G in G and H in H, then you'll see that then if it is so that if the subgroup H has the property that GAG inverse lies in H for all G in G and for all H in H, then you say that this subgroup is a normal subgroup of the group G. Okay. And the immediate exercise says that the kernel of a group homomorphism that we have met, and by this exercise we know that this is a subgroup. Okay. So it makes sense to say that, or it makes sense to ask whether the kernel of group homomorphism is normal or not. Okay. We know that kernel of a group homomorphism is a subgroup, right? We know that the kernel of a group homomorphism is a subgroup by this exercise, okay, which is yet to be solved. Okay, we know that the kernel of a group homomorphism is a subgroup. Then it makes sense to ask whether that is a normal subgroup or not, because it's because the condition of being normal applies to subgroups only, right? As of now, in fact, it applies to subgroups only. What I am aware of. So this exercise, this exercise says that the kernel of a group homomorphism is a normal subgroup of G. Okay, so you need to verify that GAG inverse. If H denotes the kernel of if H denotes the kernel, if you denote the kernel of this of a given group homomorphism by H, then GAG inverse lies in H for all G in G and for all H in H. Okay, this is something that you need to do, and then we can also consider the image. We can consider the image of a group homomorphism. That is, you consider all the elements Y inside G prime that is equal to phi x. Okay, for some x inside G, and then if you collect all such elements of G prime, in other words, you're looking at the image of a group homomorphism. Okay, so this image you have to show that the image of a group homomorphism is a subgroup of G. Okay, so usually exercise 123 and exercise 127, they are summarized as follows. We say that the kernel of a group homomorphism and the image of a group homomorphism, they form subgroups of the respective groups. So the kernel of a group homomorphism forms a subgroup of G. On the other hand, the image of a group homomorphism phi from G to G prime forms a subgroup of G prime. Okay, great. And so now you can ask that we have been discussing this notion of homomorphisms. Okay, and you have also had one example here. Is it true that given any two groups G and G prime, we have at least one homomorphism? Okay, it may certainly happen that, as of now we don't know, because if you start with a group G to G and G prime, it may not be the case that there is a group homomorphism from G to G prime, or there might be the case. It might be so that there is a group homomorphism from G to G prime. Okay, so this makes perfect sense to ask. This makes perfect sense to ask whether there exists a group homomorphism from G to G prime. Okay, this exercise answers precisely this question. This says that this exercise asks us to show that there exists a group homomorphism phi from G to G prime. Okay, no matter what this group G and G prime might be. Okay, so this is something that you need to work on. Okay, and now if we have got group homomorphisms, okay, phi and psi, phi goes from G to G prime and psi goes from G prime to G double prime. So as you see that you can compose these two functions, right? Okay, because the image of phi, okay, or this is probably called the codomain, the target of this map is G prime, and the source of the domain of this map psi is G prime. Okay, so then you can compose these two maps. Okay, this is denoted by first psi and then phi. Okay, so you take an element little g from G, and then psi composite phi of G is equal to psi applied to phi of G. Sorry for this bad handwriting. Maybe I can put it here, that psi of phi applied to G is psi applied to phi of G. Okay, for all G in G. So psi composite phi applied to G, that means you first apply phi to G and then you apply psi to what you have obtained, namely to phi G. Okay, this exercise says that composition of two group homomorphisms is a group homomorphism. This is usually summarized in that form. So so this says that psi composite phi is a group homomorphism too. Okay, so please try to work on it. Okay, and here is an interesting group homomorphism that works for any group. More specifically, if we have a group G, then the following map, this is called the identity map. Okay, this is denoted by IDG or sometimes just by ID. Okay, this is a map from G to G prime which sends an element G to G. Okay, you could show that. In fact, one can show that this is a group homomorphism. Sorry, one can show that this is a group homomorphism, and there is another related notion, another notion very much related to this notion of homomorphism. This is called an isomorphism between two groups. So it says that if we start with a group homomorphism from G to G prime, then this group homomorphism is said to be an isomorphism if there exists a homomorphism in the reverse direction. More precisely, if there is a homomorphism psi from G prime to G such that both the compositions psi composite phi and then phi composite psi, they're the identity maps on the respective groups. So here psi composite phi is the identity map on the group G. On the other hand, psi composite phi is the identity map on the group G prime. Okay. So in this situation, we say that the group homomorphism phi that we have started with is an isomorphism. Okay. Again, it's good to have an example. If you focus on this map psi from R to U to R, which sends a real number x to 1x01, then you have already seen it in the form of an exercise that this map psi is a group homomorphism. Okay. And this exercise says that this map is not only a group homomorphism, but this group homomorphism is also an isomorphism. Okay, so the notions we have met so far, namely this notion of group homomorphism and isomorphism or group isomorphism, we already have explicit examples for these notions. Okay, we have learned them in the form of exercises. Okay. Now it's your task to work on these exercises and to have a complete solution. Okay. Okay, great. And here is another notion. So if we have two groups G1 and G2, then this group G1 is said to be isomorphic to G2 if there exists an isomorphism phi from G1 to G2. Okay. There is a group isomorphism phi from G1 to G2. Okay. And if G1 is isomorphic to G2, that is if there exists an isomorphism phi from G1 to G2, then we write G1 this symbol G2. Okay, one can show that this is an equivalence relation. Okay, so if you take the collection of all groups, then one can show that this notion of being isomorphic, okay, that is, we say G1 is isomorphic to G2 if there is an isomorphism phi from G1 to G2. Okay, so in that case, this relation is said to be in that case, one can show that this relation is an equivalence relation on G. Okay, this is again an exercise left for you, so please work on it. This only amounts to unwinding the definitions that you have learned so far, or the definitions that you are learning today. We are already familiar with the notion of groups and subgroups, so that's fine. And by unwinding the definitions that you are learning today, one can solve all the exercises that I have put in this lecture. Okay, great. So just one more remark. So solving these exercises take a little while, because this is the first time you get to see these notions of isomorphism or a group homomorphism or this notion of normal subgroups. Okay, but if you go through the definition, okay, and have it just right in front of you, then working on this exercise will be will just require applying the definition of this normality, this notion of normal subgroups, nothing beyond that. Okay, so yeah, so let's move on to the next exercise. It says that if you start with a group G, and then if you collect all the isomorphisms, all the group isomorphisms from G to G. Okay, so the set of all isomorphisms from G to G, if you look at that set, then this exercise says that forms a group. Okay, the set of all isomorphisms from G to G forms a group. Okay, and now when you talk about so when you say that a set forms a group, the first task of us is to indicate the composition law, isn't it? Yeah. So we need to indicate the composition law. So the composition law is that the composition of maps. Okay. So that we have just discussed a while ago, although in a apparently different context. If we have two maps, phi and two group homomorphisms phi and psi, but the target space of phi is same as the domain of psi, then you can look at the map psi composite phi, right? So here, if you have a map phi from G to G, and here you have another group isomorphism from G to G, then you can certainly compose psi with phi, right? So this makes sense. So this is the composition of functions, okay? And then this exercise says that if you look at this set and and consider the composition law, namely the composition of functions, okay, composition of maps, then this composition law, of course, one needs to show that this is well defined. I mean, this is just a kind of observation, because this is just an observation that, I mean, you need to observe that if you compose two isomorphisms, then you end up getting an isomorphism, okay? This is something that you need to observe just to make sure that this composition law that we have in mind, that is well defined on this set. And once that is done, then you need to verify the remaining conditions, namely the associativity, and you have to, I mean, in some sense, you have to show, I mean, quote unquote, you have to show the existence of identity. I'm saying quote unquote because unless you show that something is a group, we can't talk about the identity element, right? You have to show that there is some element E, such that E star G is G star, E star EG is G star E, same as G for all G inside the, not in the group, but inside the set that is under consideration, right? And then you have to move on to the last condition, which speaks about the notion of inverse. But again, you can't use the word inverse because, I mean, we are yet to show that this set forms a group, right? Yeah. So please work on these exercises, and we conclude today's lecture here.